Morning, everybody. Pleasure to be back here. My first visit to the Institute of Catalysis goes back to the late 1980s. Imagine. Okay, that's about 30 years ago. I'm happy to meet a new generation here. I'm going to talk about the kinetic modeling and the simulation of hydrocarbon conversion processes. And, quite general slide. When you have the catalyst, in a process you have the catalyst, you have operating variables, you have the reaction network, and here come the feed components, and then you have heat transfer, and then you have mass transfer, and then out of all that you produce the products, and we have the ambition of modeling and simulating that. Okay, let's try. So what if we design commercial reactors? What are we after? We are after optimizing profit. How do we do that? Well, we have to optimize the selectivities of the desired products, and that involves optimizing the catalyst and optimizing its use in the reactor and the operation of the reactor. And to do that optimization, we need information on the kinetics of the reactions and on the heat, mass, and momentum transfer. Let's see how we intend to do that. In the very first place, if you want to do kinetics of hydrocarbon conversion, you need feedstock characterization. And here, by the way, is some information that you will find on, for instance, West Texas gas oil. And you know, the way to formulate the conversion of this, here's a fluid cap cracking model of 2007, and look how they describe the process. Gas oil yields coke, it yields gasoline and light gases. And do you really think that you can model decently the process based upon such a reaction scheme? Now come on, let's forget that and let's get into a serious approach. In the very first place, we need a detailed chemical characterization of the feed. And all the tools, all the equipment is available for that if we want to do it, and we have to. So here's high pressure liquid chromatography and high resolution mass spectrometry. With that equipment that you will find in any respectable catalysis laboratory, and you can analyze, you can separate first the VGO feed into paraffins and naphthalene and the unsaturated RO by means of high pressure liquid chromatography. These two fractions can be further analyzed using high resolution mass spectrometry. Nothing special about that. You will find that everywhere, as I said. And that yields the analysis of the paraffin and naphthenic fraction into that detail. Same with the aromatic components. You can analyze that into one ring, two ring, etc., etc. And you are now, with this analysis, at a level that I call classes level, but which is not enough yet to do the kinetic modeling as we ambition to do it. For instance, in many cases we don't have yet the analysis in the details that I mentioned in the previous slide. Can we construct a composition of an LCO, for instance? Can we construct a composition that is plausible? Well, in the first place, if we have to do that, we will choose a Monte Carlo approach. That is, we will play dices. Okay? So in that Monte Carlo approach, we select one of the elements of the 9 elements that characterize a molecule at the class level. We throw a dice, we take a random number generator, and we generate a number. And that number may be one of the 9 that characterizes molecules of LCO. And for instance, if the value of the random number generated is 0, that means there is no core, and you go directly to 7 and 8 that describes the molecules which have no core. If you select from the random number generator a value 1, that means there is a core, and you then go to 5, 6, and 7 to characterize in further detail the molecule. And since this is a Monte Carlo approach, you have to do that many times. You have to generate a large number of candidate molecules, and you go, for instance, up to 5,000. And now I have typical molecules that can be members of LCO, but with those 5,000 candidates, I don't have the real composition yet of that LCO that I am going to construct. How do I get to that? Well, I have to account for the information concerning that LCO that is available from experimental observation. And therefore, first, the 5,000 molecules that I produced by the Monte Carlo approach, these 5,000 molecules are there in equal amounts. That is not exactly what you have in an LCO. How can you now get a real composition? Well, you have to account for the experimental information that is available. And in the first place, you will make different, the mixture different in composition, and you do that. Differences means entropy, and you maximize Shannon's criterion for the entropy. So you maximize the differences between the properties of the molecules that you have generated. And how do you do that? Well, you have to account for the information which is available and the analytical information that you collect on that, on those molecules, and you maximize the Shannon criterion, accounting for the experimental information which is available. So that is a pretty efficient way of doing it. And here, for instance, we compare the POMA analysis as we have based it on the construction that we have just seen, and we compare it with the analytical POMA information that we have, and as you can see, that's a pretty good agreement between the reconstructed and the experimental, the analytical composition. And this is, by the way, work done at the French Petroleum Institute. And Jan Verstaat is a former student of mine who's working there. Well, if we now, having the information on the composition of the LCO or VGO fraction or whatever that we're going to deal with, we are going to, whatever the feed is, naphtha, VGO or whatever, if we do hydrocarbon processing on acid catalysts, these are the types of reactions that we will encounter. Alkylation, isomerization, reforming, etc., etc. Now, these processes all consist of a number of elementary types of reactions or steps, if you like. And those elementary steps are shown here: protonated cyclopropane, isomerization, beta scission, hydrogen transfer, etc., etc. And that means that whatever the catalyst, which contains acid sites, and in some cases metals, so that we get to the elementary components that will operate in those reactions. Whatever the process, we have a common approach consisting of those elementary steps. Now let us see how we deal with those elementary steps. Let me take an example, and that example is hydrocracking, and let us analyze the hydrocracking process in terms of the elementary steps that occur on the catalyst that may contain metal sites. So those are the elementary steps occurring on the acid sites of the catalyst. But in many cases, you also have metal sites. Why? Because you need to generate on the metal side by dehydrogenation or alkane hydrogenation, you need to generate the components that enter into these acid site steps. And if we want to go into that detail, in the very first place, the question is, to what detail do we need to analyze the VGO? Well, the first level is the one that leads to 16 classes, and the 16 classes consist of normal isoparaffins, naphthenes, aromatics, naphteno-aromatics. But let me draw your attention upon the mononaphthenes here. And why do I draw your attention upon that? These mononaphthenes, that's a lump. You know the word lump that was introduced by the guys from ExxonMobil. And the monosodium is a lump of metal substituted isomers, not necessarily at equilibrium. And lumping these isomers into one component leads to bias rates of the reactions and bias rate coefficients. And therefore, if we really need to do something realistic and useful, we have to decompose that further into what I call subclasses. And those are shown shown here on this slide. Here's the mononaphthenic, and I have to specify that more, as I said, because this is a lump, and I have to decompose that lump into mononaphthenic and the various isomers of those. And when I do that, instead of the 462 components that I have, when I do that, I wind up with a total of 1,262 components that I have to define by the analysis so as to come to the reaction network that corresponds with that detailed approach. And what I'm showing in this slide is just the number of monoparaffins, etc., that I have. Briefly, with that approach, I need to describe the composition of products, reactants and products, 1,262 components in the reaction mixture. Okay, we can live with that. And let me illustrate how we deal with such a complicated or such a detailed component analysis. How we deal with that in VGO, vacuum gas, or hydrocracking. In the first place, we need to describe, we need to develop the process into all those components, and that requires, of course, computer analysis, and that requires description of the components in terms of binary, in binary language. And for instance, this is a isoparaffin, and you have a methyl shift in that molecule. We go from that to that component, and we need to describe that elementary step by means of Boolean relation matrices, and you can do that just by shifting ones that describe that composition, and this is the product. And besides of this matrix, you need more information to characterize the reactants and products. You need a characterization vector on top of that binary description. You need a characterization vector saying, the hydrogen, the row 1 here says the location of the positive sign, which you cannot do just by means of that binary matrix. So you add a vector showing the location of the positive sign. Then 2, this here, row 2, tells you which carbon is positive, primary, which one is secondary, which one is tertiary. And this here is gives you the structure, but that is conventional. You call number 1 and then you have a second row here, so that characterizes the molecule or ion that you are dealing with. Something wrong here. Now, if you analyze the feed and the product in terms of elementary steps. You have to go into the details of these elementary steps, which are shown here, something like 13 or 14. And there are 13, 14 elementary steps here, and you have to account for all those possible steps at each level of carbon that you are dealing with. So if you do hydrocracking, and you come from C40 down to the lower hydrocarbons, well, at each carbon level, these are possible elementary steps that you have to consider. And so you can imagine that when you come down from 40 and you go down to 3, 4 carbons, that is quite an effort. Indeed, it takes hours and hours of computing to generate that complete reaction scheme. And of course, you do that with computer. And when I deal with hydrocracking and with VGO hydrocracking, all I have plotted here is the number of elementary steps of the various types that you encounter, and that goes into the millions. And what I have shown here in this slide is the number of carbenium ions that are involved into that reaction scheme. As you can see, that goes into the millions. So generating the reaction network is a big job. It's a very big job. But you need to do it only once for a given VGO that you are dealing with. Now, having done that, we will now get to the rate coefficient, and in that, for given elementary steps, I have to account for the effect of structure. How am I going to do that? Well, they've done that for us many years ago in transition state theory. And when I look at transition state theory, how is structure defined there? Well, by means of what they call the symmetry number. Let's look at what that means. In transition state theory, this is the rate equation. These are the partition functions that reflect the entropy of the step. And each of the and these are the concentrations, of course, and that's the activation energy. And each of the partition functions of the reactants and of the active intermediate consists of those 4 contributions, and transition, rotation, translation, electronic, etc. And if I want to account for the effect of structure on the rate coefficient, well, the most obvious among those entropy contributions is the one dealing with the rotation. Because here you can see that this contribution of the rotation explicitly contains the structure, the symmetry, the structure of the involved species. Okay? When we look at the rotational contribution to the symmetry, we see there is an intrinsic value, and there is something that is related to the structure. So there is a delta symmetry, as you go from a component A over the intermediate, that is given by this formula. That's just transition state theory. What we do now is we will, knowing this, we will extract that out of the entropy contribution to the rate coefficient. And this effect of symmetry extracted out of the entropy is this ratio of symmetry numbers, and I have called that the number of single events. So we have extracted the effect of structure out of the rate coefficient. And what is left after extracting that, what is left is what I call the single event frequency factor. And that single event frequency factor is unique for all the terms, for all the reaction, all the elementary steps of all the components of a homolog series. So we have this number of single events, we have the entropy contribution, and this is enthalpy contribution, and we didn't have to invent anything there. That is well known. That is related to the structure through the Evans-Polanyi relation that was derived in the 1930s, 1940s. And that is this Evans-Polanyi relation that I referred to, and that says that the activation energy is linearly related to the heat of reaction. And the heat of reaction is a property that is well documented in the literature and that you can find in any book on physical chemistry. So again, having expressed the rate coefficient in this way, I mean extracting the ratio of the symmetry numbers of reactant and intermediate, I have the single event frequency factor that I can calculate or get from experiments. I have the number of single events that I can calculate, and I have the activation energy that I get from sources in the literature. When you do this complete analysis, the way that I outlined it, for VGO hydrocracking, I need this number, something like 32, 33 rate equations, and it was possible to determine in a reliable way these 33 experimental values for the rate coefficients for the hydrocracking of VGO. The way that you get the experimental values for that, I want to draw your attention upon this, because if you talk to many industrial people, they will tell you, the boss will tell you, listen, your experimental equipment has to be a minimization of the experimental, of the industrial reactor. I want you to do experiments in a reactor of the same type. Forget it, that doesn't make any sense. You do the experimental investigation to get the rate parameters. You do that in an optimal way. And that does not mean necessarily that you use the same type of reactor as the industrial reactor. You use the most appropriate type of reactor to derive the rate equations. And the industrial reactor will come up then in the modeling and in the simulation of it. What I'm showing here is the type of equipment that we have been using and that I think is a very appropriate type of reactor is the Robinson-Mahoney reactor, where you have recycling of the liquid and the gas in the reactor in such a way that you operate at one concentration and one temperature. And that permits you to get decent values, point values for the reaction rate, and from that, you get, of course, the rate coefficients. This is a VGO analysis by high resolution mass spectrometry, and it shows you the detail that at which you can reach by means of this analysis by high resolution mass spectrometry. And that is, using that approach, shows you the hydrocracker feed for a second stage hydrocracker. Yeah? That is typical feed that you have, shows you the total amount of components that are required for a decent description of the VGO. And here you have the composition of such a VGO feedstock with the various types of components that you have in there. And that is determined the way that I just outlined. And this is the product distribution of hydrocracking at a given temperature, etc. And these are compositions that you obtain in that process. As you can see, you have a quite decent agreement between the experimental and the predicted based upon the rate coefficients that I have mentioned. So you can see you do a pretty decent job with this approach. Now, let's go to the next final step, which is the reactor modeling. And that has to account for reaction, mass transfer, heat transfer, and momentum transfer. Question is, at what level will I deal with those phenomena? Okay. Am I going to go through the rigorous application of the conservation of mass equations, total continuity equation, solid phase, total continuity equation for a species in the gas phase, for that species in the solid phase? I can go on like that. I will just skip the equations because that is just too much. At a certain stage, you will have to make a selection about the rigor that you're going to apply for the reactor simulation. We have to be realistic. I'm an advocate of going as far as you can in the detailed description of composition and process, yeah? But at a certain stage, we have to be realistic and realize that we cannot go on like that. So the question is then, how, if I do not follow that rigorous approach that I've just outlined, what is the model that I'm going to use? Is there a realistic approach that we can follow? Well, when we look at the literature, you will find that we describe the hydrocracking in a multi-phase reactor model, of course, and we need, of course, continuity equations for the gas phase and for the liquid phase components, and we have to account for energy equation for gas and liquid phase, and we have to account for the transfer of mass and energy between the two phases. So that's the model that we will apply. It is not as strict as I outlined, but we have to be realistic. And we have what is called a trickle bed reactor model, and you have a continuity equation. You have continuity equations for the gas phase components, saying how they change along the reactor, and they change because of transfer from the gas phase to the liquid, and then you describe the change in the liquid phase, which is due to the transfer from the gas phase, and the liquid, and because of reaction, and we associate liquid and surface of the solid catalyst. There is no mass transfer limitation considered in this equation. So this is the rate at which the component A is disappearing out of the gas phase through transfer to the liquid phase and reaction in the liquid phase. And this, of course, describes how the temperature evolves in the reactor. That's not a small thing, you know. You have 1,266 components here, and you have hydrogen, and you have two phases, so you have 2,534 maximum, 2,534 component continuity equations that you have to integrate. But there are methods to do that, and here has proposed very efficient methods to do that. The result is you have everything that you want to know about any components in the feed that you want to follow, and I'm just selecting here the profiles of the alkanes going from C5 to C16, and the profiles of these alkanes in the reactor. This is the concentration, and this is the distance in the reactor, and what is shown here is just for C21, and how the various components vary through the reactor. And you can see here the green components, that's this here, and the red ones that disappear through the reactor. And you can see for instance, again, concentration profiles of C23 structures through the reactor. Yeah, that's just one piece of information, just to illustrate the amount of information that you can generate through such a model, and the amount of information that the engineering department of the refinery or the oil company that they can use to propose better optimized profiles and operating conditions of the refinery reactor. I think that is the last slide. So just summarizing, what have we been doing? What can we do presently? Well, we can consider kinetics, thermal continuity equations, energy momentum equations, and we need mathematics and optimization routines which are available. And when we combine the two, we can do modeling and simulation, and in fact, we can call what we have done, we can call that virtual processing. Okay, that's all I wanted to say. Thank you.